Hello. Here we discuss image formation using a concave mirror. A Before we begin, let's draw the ray diagram. By begin, I mean instead of going in the order of A, B, C, D, E, F. Let me start with the last part where they ask you to show the ray diagram, and that helps us to make sure that everything is consistent. Whatever answers we get, it should come out consistent. Ray diagram involves drawing uh, everything with reference to an optical axis, which is the direction of light. So that's the direction in which light is moving, and we call it the optical axis. The mirror will be, for our purposes, this line will represent the mirror, but of course, we have a spherical mirror, a concave mirror for that. And this line represents the, oops, not good. So that's our concave mirror. Again, this is exaggerated version. The straight line for drawing purposes, we should use the straight line. Where is the polished part of the mirror? That's in this direction. This hairy structures tells you that's the unpolished part, sorry, and the polished part is in the direction in which the light falls. So that's our concave mirror. So this focal length is measured positive to the left and negative to the right. That is in the direct optical axis, you measure it negative. And a concave mirror has a positive focal length, and a convex mirror has a negative focal length. So that's the idea. Object distance are measured negative in the direction of the optical axis and positive in in the direction opposite to the optical axis, and q being the same. In fact, everything is measured positive in the direction in which light is coming from. But in the case of lenses, this will change. So we are highlighting this part here itself. So whenever the object is negative, it's called a virtual object, which is possible using compound mirrors with more than one mirrors. But here we restrict ourselves to real objects. So object is placed in front of the mirror, that means it's a real object. Same thing if an image distance comes out to be negative, it will be called a virtual image, which is basically an image that is formed behind the lens. And otherwise, it's a real image. A real image, an example of a real image is what we see on a projector screen where the light actually passes through that point. And a virtual image is what we see whenever we see ourselves in a bathroom mirror. Okay, so again, we have a concave mirror, and it has focal length of 10 centimeters. So that's the 10 centimeters we will have. So that's our 10 centimeters. That's the focal point, and double the distance. So I'll try my best to be reasonably correct. So that's you should use a ruler. This really matters, and this can change our results significantly. But I don't think I have a. What is that? Let me not try them. So 2 times the focal length on is the radius of curvature, and that is the same scale we can draw to the right also. And this is one focal length, and that's two focal length. Okay. Object is kept 5 centimeters. So if focal length is 10, so it's exactly half of that is 5. So that's somewhere here. And we have an object that's placed upright in front of the mirror, and that's our object. And its height is 1 centimeter, so that forms the scale of 1 centimeter for our purposes. We have to, ray diagram involves drawing two rays and figuring out where they intersect. First ray is passes through the radius of curvature. So let me draw a reference line to begin with. So it's going to be my reference line, let's say. So that's pretty much, and I have to go the opposite direction also. For that, I will start from the head and go this way. Okay, but that was just a reference line to show the actual path of the ray. The ray begins from the head of the object and travels to the mirror. It actually goes only till here if we were to assume the mirror is in there, but we agreed that in this is a artifact of the zooming or the choice of the scales. We should use the straight line as our reference. So that's our mirror. It reaches all the way till here and reflects back. When it falls on the mirror, this is a sphere. That's the center of the sphere. So we are going along the radius. A radius is the normal ray itself. So the angle of incidence is zero. So angle of reflection will also be zero. So it actually traces back itself. So that tracing back will be shown this way. So that's tracing back the original ray itself. And that's the direction here. So that's ray 1. Again, it starts from the head, goes and hits the mirror. Since it's the radius of the sphere, which the mirror is part of, angle of incidence is zero, angle of reflection is zero using law of reflection, and thus is traces back where it came from and goes through the radius of, or the center of curvature, which is uh, represented by the point R. That's one ray. The second ray, for the second ray, we actually start uh, with a ray that goes parallel to the optical axis. So again, start from the head of the object and follow a ray that goes parallel this time. So that's a parallel ray, and its direction is represented by this arrow. After it hits the mirror, again, we have shown the straight line to represent the mirror. It converges to the focal point. All the rays that come and hit parallel to the optical axis for a spherical mirror goes through the focal point. That's a conclusion of the geometry of a sphere. To achieve that, I draw a reference line, this time starting from the focal point and going right here. Okay. So that's all. And I can actually go this way too. Oops. So that's my focal point. Okay. So that's the reference line. This time let me show the actual ray. Here it goes and hits the mirror, and after reflection, it goes through the focal point. That's what the ray does, and this is the direction of the ray, and that's ray 2. Wherever these two rays meet, that's where the image is formed. But it's clear that since it's diverging off, it doesn't seem like these two rays are meeting, but instead they seem to be meeting somewhere at the back. So we project these two rays wherever they seem to be originating from, in a sense. And wherever they meet, that's where the image is formed. And that will be here. So that's the image. Seems like it is exactly about 10 centimeters onto the right on this. I know the answer for this problem. That's one the way why I'm saying that, but we will see that it indeed works out that way. So let's work on the problem. But before we proceed further, we can conclude various things. It is behind. The image is formed bigger, first of all. It is upright and it is behind, which means it's a virtual image. So it's negative. It should come out as a negative answer. So let's proceed and see what we get. Part A, what is the mirror's radius of curvature? R is 2 times the focal length, which is 2 times plus 10 centimeters, which is plus 20 centimeters. Plus is measured to the left, so it is radius of curvature. It's this point here, which we already used in drawing the ray diagram. Calculate the image distance. The formula is 1 over p, 1 over p plus 1 over q. The inverse of the object distance plus the inverse of the image distance should be equal to the inverse of the focal length, which gives us 1 over object distance is plus 5. It is kept in front. Uh, Plus 1 over q is equal to 1 over plus 10 centimeters. Object distance is given to 2 sig digits. So this is 1 over q is 1 over 10 minus 1 over 5. Multiply by 2 here. That gives us 1 minus 2. So it's minus 1 over 10. But this, or let me write that here. So that's q then is equal to minus 10, 2 sig digits, because 5 is given only to 2 sig digits. So it's 5 minus 10 centimeters, which is what we find here. Minus means it is behind the mirror, and 10 is this point, which is which again I expected it to find it, so I was, even without a ruler, I was trying to make sure that the image comes out there. But that's the whole point, that even a small error in these distances can lead to significant amount of error by forming the images. Part C, what's the magnification? Magnification is negative of the ratio of the image distance to object distance. So that's negative of image distance is minus 10 centimeters, and object distance was plus 5 centimeters. Centimeters cancels, and the magnification is plus 2.0 without, and does not have any dimensions. Plus means it is upright, it is indeed upright, and twice means its size is 2 times its object distance, which is what roughly the diagram seems to be justifying that number. D, is the image real or virtual? Image distance came out to be negative, so it's virtual according to our sign convention here. Virtual image means it should be negative. Okay. Part E, is the image inverted or upright? The magnification came out to be positive, that means it will be upright. The positive magnification means it's upright. Negative means that it's an inverted image. This can be again verified with the actual height of the image. Height of the image satisfies magnification is equal to height of the image over height of the object. we found the magnification to be plus 2.0 is equal to height of the image over height of the object was plus 1.0 centimeters. So this implies that height of the image is plus 2 centimeters. Plus sign stands for it is upright, and size is actually 2 centimeters, double the size of the object, which is consistent with the diagram. Let me stop sharing here and stop the recording.